So what'd you guys do to get ready for today? Somebody tell me, what'd you do to get ready for today? Because what I did was I watched the lecture for this lecture from last term, and then I listened to some music that would get me excited. So what'd you do? You listen to music? What'd you listen to? Bollywood songs. Are they like exciting and kind of get you going? Bollywood songs? That's pretty cool. We need some. So I normally. So you're the one that ran on the track last time. To get ready for class. Oh, sitting in front of you, who's not here now. Must have drowned. Oh, who ran on the track to get ready for class? Talking to his neighbor guy. Not even paying attention to me right now, guy. Totally just not even paying attention to me right now. So you're the one that runs on the track to get ready for class. Did you do that today? You did this morning before lab. Was it wet? It was, yeah. So I totally was laying in bed at 3:45 this morning, listening to the rain, thinking, well, I'm not going to go back to sleep. And I'm not going out there. So I'll turn on an audio. And it was, I did the Audible Plus thing or whatever. So it's like $14 a month and you get one thing plus whatever they give you for free. And so the title of the book was The Reluctant Druid. It's some guy that gives away his books for free on Audible. Because I don't get another credit for a couple weeks. I'm still listening. I mean, not right now. This was a song to get my blood flowing. But now I'm gonna just make sure that we're live on YouTube before I do this my channel and play, because I have had many times. Can't hear the lecture. The video is too loud. I'm gonna do this video that you guys can't hear. It's because we can't hear it in the room. But I think I stopped all that. Fact. There. They're gone. So obviously the audio works because somebody else was having trouble hearing the lecture because the video was too loud. I'll put these away. I don't like podiums. I mean, they're cool if you guys are shooting at me, right? But I have not had a death threat in a while from a student. And they are cool when there's people in the back of the room giggling, when I'm walking around and there's people up in the back giggling. And I got to wonder, why are they giggling? So I go behind the podium and check my fly. But that's the only reason I like podiums. And I'm sorry this room has such a big podium. And I'll try to ignore it, but also try to stay on camera. So CNC machining and prototype manufacturing. First off, for the class, why? It is really cool. And your shirt doesn't have your name on it. You promised.
It's in Japanese.
It's in Japanese.
Instead of saying Prior Waskin, it says Pudaya Wasikin.
Pudaya Wasakin.
But don't worry, I got another one on.
You know, Heroin Kid used to be my favorite ME1800 student, but you're running a close second now. Someday ask me about Heroin Kid. It is cool. But, all right, so the lecture title implies two things, right? CNC machining has three things, right? CNC, machining, four things: prototype, and manufacturing. So we're going to talk about four things today. There's only 40 something minutes left, 42 minutes left or something like that. All right, so first off, what the hell is CNC? That's the first thing on the list. What is it?
Computer numerical control.
Computer. Oh, this is good chalk. Now that's what he said. I've never said numerical. I always just say numeric. But what the hell does that mean? All right, so can anybody envision a computer that doesn't use numbers? All right, so we can just say that this word is redundant, right? I mean, that's what the N in CNC means. It's numeric, numerical, but it's really redundant. Computers use numbers. So it's actually historical. They started with numeric controlled machine tools, NC machines. They were totally using computers. It was just before we used computer as a common word, right? It was before computer had entered the vernacular. And so they were NC machines because they were using numbers to control where the tip of the tool went. That's all it is. It's using a computer manipulating numbers to control where the tip of the tool goes, because we want to do machining with the tool. Anybody know when they invented the first NC machine? When and where? Anybody know? Really? Because it wasn't that far from here. You could drive there in about 35 minutes from here. I mean, all right, 45 minutes because you got to get to the car. Anybody? Yep. It was not in Lowell. They did a lot of weaving in Lowell, a lot of textiles in Lowell. First NC machine was made at MIT Lincoln Labs. I know. Friends don't let friends go to MIT. It's totally cool to let your friends work there afterwards. So it was MIT Lincoln Labs. All right, so now I've told you where the first one was made. Anybody know when? Take a guess. Give me a decade.
The 70s?
It was before the 70s. 20s. It was after the 20s. Now we've bracketed the target, right? Anybody Army ROTC? How about Navy ROTC? Really? Anybody in ROTC here? No warriors in the class. Well, so the artillery guys, whether they're in the Army shooting their howitzers or they're in the Navy shooting their big guns on the ships, they want to bracket. Well, actually, no, they just want to hit the target. But typically, you shoot one as too short. You shoot one as too long. Now you know the target's in between, right? So we've bracketed the target. It's between the 20s and the 70s. Who's going to average it and make a guess? Close. 1947. 1947, MIT Lincoln Labs. Why did they build an NC machine tool? Besides the fact that they were nerds and they could. Right, because nerds like to build shit. Yeah, Cold War. We build a lot of stuff because of wars, whether they're hot or cold. They had a specific manufacturing problem they needed to solve. You couldn't solve it with Etch-a-Sketch style machining. So who's used an Etch-a-Sketch? Pretty cool. Who's ever held a tablet computer and shook it to try to make it reboot? If you used an Etch-a-Sketch a lot, you have. especially when you're really frustrated because it's a Windows-based tablet, and it's unlike really frustrated because it's a Apple-based tablet, in which case you might as well just curl up and go to sleep because there's nothing you can do to affect the outcome. Anyways, they had a really specific manufacturing problem that they couldn't solve by turning knobs. What was the problem they were trying to solve? What else did we develop around the late 1940s, early 1950s?
Atomic bombs.
Yeah, the atomic bombs. We figured that out totally without CNC machining. Jet engines. It was a lead up to jet engines. I mean, we were doing jet engines about that time. But it was to make the airfoils for helicopter wings. And so you know that on the helicopter, the spinny bit is the wing, right? And so how fast is the tip of the helicopter blade going? Yeah, very is a demonstrative term. What's the equation that would calculate the speed of the tip of the helicopter blade? Besides around the speed of sound, which is a big deal when you're making materials that are going to live through that shock wave thing. What's the equation? You guys know this. It's like 7th grade math. So we've got, what is it, R cross omega? No cross. R dot omega times. So radius. Is it radius? The length of the blade. So if we had to derive the equation, and so this is a thing. You guys know I can't spell, right? So I don't know if it's a corollary to can't spell. I also can't remember equations. But I'm wicked smart. In fact, I had some smart water this weekend. So I'm even smarter than normal. But I am wicked smart, and I can derive equations. So what's the thing we're trying to solve? It's the velocity of a point, right? Right, so we've got a point, and we're trying to figure out its velocity. We know the motion that it's going to take, right? It's going to do this. Years of practice, let me tell you. I remember watching that 7th grade teacher do that, and I was like, how does he do that? Years of practice. So we get that point. We know the motion it's about to take. It's got a velocity in this direction, right? So what's velocity equal? Yeah. So it's yeah, so let's look at the units. So it's length times time. It's divided by, good, because I drew the divided by even though you said times. Time. That's all right. That's all right. That's why we're doing it out loud. And so, did you all know, or did you all know, engineering's math? Just a bunch of word problems. Cancel the units. So it's length times time. And so where do we get length here? Which length is it times time? Yeah. You had your hand up.
Okay, cool. It's the circumference of the circle.
So the circumference, that's the distance that it travels, right? That's a length. So it's distance. And what's the time it takes to travel one rotation? Is it RPM? So it's revolutions. Now you could do the R and the omega, but this is easier for me to keep in my mind because I'm still pretty sure it's R cross omega because velocity is a vector. So I'm pretty sure it has to be a cross product. But I don't know. This is why I don't memorize equations. Right? This is why I figure them out every time. But it's length times time. The length is the circumference. So what's the circumference of our circle? So we're talking about helicopter blades now, right? But it's really important in machining too. It is the most fundamental equation in machining that we're deriving right now. So just because we're talking about helicopter blades, would you believe that a helicopter could be used to do machining? Would you believe it's not good for the helicopter? Yeah, but you can totally use a helicopter to do machining. In fact, I saw this really cool. I saw a video on YouTube once where they were interviewing helicopter pilots from the Vietnam era, and there was anyway, there was a guy on the ground that needed to get picked up, and there's no helicopters that wanted to go in there, and the helicopters that finally showed up, they're like, well, we can't fit in there, right? There's not enough room for us to get down low enough for somebody to get in the helicopter. And then the special forces guy, held a gun on the helicopter pilot and says, you will go down and pick up my friend. And so they did. So they went down and cut up all the trees with the ends of their helicopter blades, right? And they went down there, they picked the people up. So you can do machining with helicopters. Not highly recommended. But anyway, so we got circumference, right? So what's the equation for circumference? 7th grade math? It's 2 pi r. I just like to call it pi d. So pi times diameter. And what's the time? We said that already, right? RPM, revolutions per, no, is that distance per revolutions per minute? Because we want, is this right?
Well, it's like the revolution is.
Well, so this is length per revolution, right? And we've got revolutions per minute on the bottom. And so what should our revolutions per minute be? I don't know, pick a number. Doesn't matter. This is RPM in rev per minute. And so when we divide that, but that's length times minute, length times time, meters per second. Do we have the units right? No. So what do we have to do?
Multiply them, not divide them.
In rev. Then we get length per minute, length per time. I like that. All right, so when length gets bigger, velocity goes up. When RPM gets bigger, velocity goes up. That intuitively makes sense too, right? So it's not just a matter of cancel the units. Make sure it intuitively makes sense. All right. So anyway, they wanted to make airfoil shapes that could go through the wind at the tip of helicopter blades without falling apart in order to, I don't know, better kill people or save them, depending on which part of the battle you're in. But it was all about, somebody said Cold War. Yeah, Cold War, end of the World War, Korean War, one of those things. All right, so they invented it, Lincoln Labs, MIT, cool stuff, CNC machining. But what's machining? And when did we start doing machining? So who was the first machinist, do you think? Roughly what era did the first machinist work? I guarantee it wasn't at MIT Lincoln Labs.
Just to take a shot in the dark, Europe during the Enlightenment.
Really? You think it was that late in human history? How about, yeah.
Caveman, like working on his rocks.
Yeah, how about the first caveman who took one rock and hit it against another rock? Right? Who knows? Actually, his name was Fred. He was a really nice guy. Who knows who it was, right? But we've been doing machining. So what is machining then? So you took it to mean like with a machine tool. Yeah, I meant for people to take it to mean that way so that I could get them to be wrong when they answer the question, so that I could get a second person to talk in the class. This is really boring for me when only one person talks in the class. So what's your name? Tucker. Tucker. And this is the guy that always has his name on his shirt so we don't have to remember it. Except it's in Japanese now, so who knows? Wait, no, it's the other one. I can't. It's too.
It's a wonky font.
It's like pry something. It starts with a P. Prior. Right, like the priest. Tucker, Prior. I forgot all the rest of the names. But I get Tucker and Prior today. All right, so machining is, so basically what is machining then? Yes. If it's the caveman chopping stuff off, what is it? Well, so manufacturing is making something out of a resource. You added using a tool, and we do typically use a tool to do machining. I don't think you can do machining without a tool, so yes, it requires a tool. But machining is making stuff by removing material. Right, so if you want to go to the most basic definition, it's making stuff by removing material. And so the guy that's who's heard the fable about the art student that asked his teacher told him to carve an elephant out of a block of ivory. Let's say it's ivory. That would be kind of redundant, ironic. Yeah, out of a block of whatever material, soap, stone. So the student says, but how do I carve an elephant out of this block of soap, stone? And the teacher says, what? Really? Anybody? Cut away everything that's not elephant. Right, so in machining processes, we cut away everything that's not the part we want. So it's a material removal process, yeah. Not by this definition. It uses similar technology. And so 3D printing is an additive manufacturing process, and it's more like casting. Actually, it's very much like casting. And then we have changing manufacturing processes like forging, where you just smash that stuff with a hammer until it's the shape you want it to be. I mean, you could shape the hammer to be specific shapes. And those are kind of so we can take materials, so and we often call it billet machining. We take a billet of material, a chunk of material, and we cut away everything we don't want. So that's like the guy making an elephant. Then there's forging. That's like the guy banging on a piece of steel to make a sword. And then there's casting or 3D printing and these other additive tools that's, what is that like? What's a historical reference to that besides casting? I don't know, it's like, oh, it's like making a popsicle. Right, you pour it into the mold, you let it freeze, it becomes the thing you wanted, and then you eat it. Yeah, okay. So in this class, we're going to talk a lot about CNC machining. Anybody know why? We talked about this already. Because we have CNC machine tools here. Because we think we're pretty good at talking about CNC machining. And the most important reason, because I said so, is because CNC machining is the most prolific manufacturing process in the world today. So there is nothing that you use on a daily basis that's more than 2 steps away from a CNC machine tool, except for the things that are 3 steps away. But most of them are 2 steps away. So like this tabletop, right? So probably nobody used a CNC machine tool to make the tabletop. 100% they used a CNC machine tool to make the parts for the machine that made the tabletop. That's what I mean by 2 steps away. My shoes, I couldn't find my shoes this morning. I really didn't want to wear my new leather shoes in the rain anyway, but These are like taped and glued back together. So there was the tape that's holding the sole of my shoe together here. That was it was cut by a scissor. Definitely the scissor was made using CNC machine tools. These are kind of worn out, but you can see that there used to be a shape on the bottom of the shoe. So the mold that made that shape, that was made with the CNC machine tool. Really, I was like looking underneath the couch and everything. I couldn't find my shoes this morning. Don't know where they are. Don't think the weekend was that much fun, but I guess maybe it was. Who knows? All right, so CNC machine tools. So machining is just removing material. The kind of machining we're going to talk about in class today, in the class, throughout the class. So I talk about this, right? Which is material removal. You can't see that. Let me fix it so you can see that. So the kind of machining we're going to talk about is material removal by large chip formation. Now, the chips that we're talking about are going to be like, I don't know, a few thousandths of an inch thick and maybe a few hundred thousandths of an inch wide. So large is a relative term here, right? But material removal by small chip formation is things like sanding. Who's ever used sandpaper? Most of us have used sandpaper. So the little bits of material that come off when you do sanding, those are chips. They're formed exactly the same way the chips are formed in the machining processes we're going to use in the mills and the lathes we use in the lab, except on a piece of sandpaper, there might be 10,000 cutting tools. In a turning operation, so who knows the difference between turning and milling? You do. What is it?
Turning, you have the materials being spun, and milling the cutting.
Right. So in turning, the workpiece rotates. So the workpiece spins around, and the tool moves in and out relative to the center of the workpiece, and it moves along the axis of the spinning workpiece. So with a turning operation, you can make axisymmetric parts. It's like, who's had a CAD class? Like the Introduction to Drawing East 1310 or whatever we call it, right? So in that, you do a revolve operation in the CAD software. So you make like an outline and you revolve that around and it makes a part appear. So parts that you made using a revolve operation, typically you'd use a turning operation to carve away the bit that is an elephant. So turning. In milling, the tool spins and the prismatic workpiece moves relative to the tool, or the tool moves relative to the prismatic workpiece. And it's really that relative motion between the tool and the workpiece that matters. So in the diagram we have here, if I draw it on the board, right? So we've got workpiece, chip, tool, more workpiece here, right? And so somewhere in here, that's chip. This is workpiece. So the cutting edge of the tool is right here. We're looking down the cutting edge of the tool in this diagram. So right along that edge. And the workpiece is moving that way relative to the tool, or you can say the tool is moving that way relative to the workpiece. So that's how all chip formation works. Who in the room has done chip formation before? Who in the room thinks they have not done chip formation before? Nobody's willing to be brave. You're thinking maybe not? Or he's willing to wave his hand but not quite raise it. Have you ever had toast?
Yeah.
Do you like butter on your toast?
Not particularly. More of a jet.
Do you like butter on anything?
Yeah.
All right. Have you ever applied the butter yourself? So you've done chip formation. if you've used a knife to cut butter. It's the same physical process. In fact, I'll share with you a video I did. I had my daughter help me with an experiment during the COVID times. And we took a machine tool, cutting tool, and we used it to cut some butter. So it's kind of like when you're like, it's like when the stick of butter is hard. And we've all experienced this, right? Somebody, you took it out to soften it up because you were making toast. And then in my case, your wife puts it back in the fridge because she doesn't like to see stuff sitting on the counter. And you're like, but I was waiting to make toast. And you can't say that to your wife because she looks at it like you're stupid. But the butter's hard and you got to like skive it off the top with a knife. So that process of like the butter knife and the hard butter and skiving it off the top, that is identical, if you zoom in on it, to what happens in the CNC machine tool when you're machining the parts. Yeah, we said that. It's written on the thing. See, I told you that the slides do line up with the things I say sometimes. So here's zoomed in on that. And I apologize if there's audio for the people at home because we can't hear the audio here, and you probably can't hear me talking if you're at home, if there is audio. But, and so if we pause this here. So in this right here, so this is the cutting tool. So we're doing a turning operation. You guys can see that the workpiece is turning. So we're doing a turning operation. We do turning operations in the lathe. We do milling operations in the mill. Some people call turning lathing. And that tells the rest of us that they're like a kid with CAD. They haven't learned the technobabble, right? So call it turning, even if the other people are calling it lathing. You'll be the smart person, and at least you will know that. So in this case, we're turning the face of the workpiece. The end of the workpiece in the lathe is always called the face. So we're turning the face in the workpiece, and we're reducing the length of the workpiece. That wasn't what was supposed to happen. Here, let's try again. All right, so we're turning the face of the workpiece. The bit that's spinning around, that's holding the workpiece, we call that the lathe's chuck. The chuck in the lathe. The bit that's doing the cutting, we call that the tool. So the tool's feeding across the face of the workpiece. In a second here, we're going to zoom in. There we are. We're zoomed in on that operation. And so you can see, as you look at it, that there's the workpiece moving past the cutting edge of the tool. Some of the workpiece is sliding up the edge of the tool, and some of it is going past the tool, right? The bit that's sliding up the edge of the tool, we call that the chip. Those are those things that are, a few thousandths of an inch thick and, a few hundred thousandths wide. The width really has to do with how deep you put the tool into the workpiece when you do this. And then next week, we'll come to see that region right where it stops being workpiece and starts being chip, that's important. That's where the shearing has happened. That's where the individual grains of the material are sliding relative to each other. And it's starting to do that. And we'll talk about the energy there. But anyways, all right, so that's turning. Let's take another quick look at turning with a different view. So can you guys see that? Kind of. I'm going to zoom in. I think the people at home can see that too. Okay. So you can see that. So that's the tool. So in our turning operation, this top of the tool here, that's called the rake face of the tool. That's going to be important to us later. And this is an outside diameter turning operation. We're feeding through the workpiece. And here it goes. Turn on the feed. Turn on the feed. There it goes. And so that chip forms right there as it goes across the top of the workpiece.
Ready to go.
Stop. Escape. And here's the milling operation. So milling operation, the physics are the same. The physics in a milling operation are the same. It's still the cutting edge of the work of the tool passing through the workpiece. But now the tool might have, this wasn't the best video. Here we go. Now it's milling. The tool, this particular tool has, I think, 4 cutting edges. The tool is rotating, and then it's feeding sideways through the workpiece to make the shape. So this is a milling operation. Milling operations tend to make prismatic shapes, stuff that you can clamp in a vise and hold on to. And so again, it's material removal by large chip formation. Wow. You probably, did anybody just watch the recording of last lecture before starting? Like I did. Oh, by the way, if you watch these videos later, I recommend 2x speed. 2x speed is way better than regular speed. And if there's something you think you missed something, you could always go back, right? And you could slow it down. So in the, I said, oh, wow, because I just looked at my watch and saw what time it was. And it was exactly the same minute of the hour that I got to this point in the last lecture. And I took a totally different path in the last lecture. But at this moment, I said, good. We have 10 minutes left to talk about prototyping, right? Because prototype, so CNC manufacturing and prototyping, right? So what is prototyping? And why is it important in manufacturing? Yes.
So prototyping is like, it's like where you build like a bunch of different test pieces.
Doesn't have to be a bunch, but sure. Prototyping is where you figure out, can I make it? Right? So you can think you know you can make it, but you don't really know you can make it until you've made it. Does that make sense? The other reason we use prototyping can be to see, can we do the manufacturing process we want to do? That's one reason. The second reason we do prototyping is, what's manufacturing again? It's making stuff with the intent to sell it. Second reason we do prototyping is to find out if anybody wants to buy it. And it's really hard for people to decide if they want to buy it when it's just an idea, when it's just a concept that you're describing to them. Actually, some stuff it's easier to sell if you don't actually have it, but that's the stuff that you can't actually make. The stuff that you can actually make, it's almost always easier to sell when you can hand it to somebody and they can hold it in their hands. So we do prototyping for 2 different reasons. To see, can we make it? And to see, should we make it? But it's making 1 to 50,000. It depends on the scope of the prototyping, right? But it's making some initial pieces, also to see what's the best way to make it. We might try several different methods to make something before we decide what's the best way to make it. We might not really know that. What do we call it when we try multiple things to figure out what's the best? Experimenting. So we might experiment, and that's actually, so we said this class was going to be about engineering science so manufacturing, engineering, and science, right? So some of the science part might be making prototypes to find out what's the best way to make something. So we do prototyping to find out, can we make it? Should we make it? So did anybody go on a tour of WPI before they became a student? Did anybody get a chance to go into the manufacturing labs on their tour? Much fewer hands. So it used to be one of the normal first stops on the tour groups, and we loved that because people would come back and say, I came to WPI because I went on the tour, right? And so that always makes me feel good. And then they stopped doing that because of COVID and because they're lazy. Anyway, so you said you came on a tour of the labs. Did you talk to somebody that worked in the labs when you went on the tour? You did? We are a showroom for the Haas, for the HFO, local Haas factory outlet. That's part of it. We also, did your parents ask any questions? Yeah. So I was probably talking to her dad or somebody just like him, because it was years ago. Came in and says, "Hey, do you guys do any rapid prototyping?" Yeah, it wasn't your dad, because this was like 8 years ago, and you don't look like it took you that long to get in. But do you guys do any rapid prototyping? And I knew he meant 3D printing. And it was right when like the first TED Talks about 3D printing had come out. By the way, do you guys know when 3D printing was invented? It was in the 80s, 1980s. So people have been doing 3D printing for a long time before anybody did a TED Talk about 3D printing. But anyways, he's like, do you guys do rapid prototyping? Because he was all excited because he wanted his kid to go to the place where they did rapid prototyping. And I knew that's what he meant. And I said, well, hey, 1/2 inch deep, 1/2 inch over, 800 inches a minute in aluminum. I think that's pretty fast. So we do fast prototyping, but I don't know about rapid. Anyways, so a lot of times you can use 3D printing to see, is the shape right? Do the parts fit together? But when you get to that, can we manufacture it part, you actually need to use the manufacturing processes that you're going to use to make the parts later. So that's why we'll use CNC machining to do rapid prototyping. It's actually, I don't know, those 3D printed parts. We'll talk more about this later in the term, but they don't behave. The material itself doesn't behave the same way that the materials we use in machining tend to behave. With that said, now we're often using 3D printing to make near net shape parts, so that we don't have to remove nearly as much material. So like a wing spar on a fighter airplane, those can be billet machined. So a big long piece of material that's a forging to start with. So they forge the material and stamp it into something. Then they do like 99% material removal to get rid of most of it. Well, that's expensive. So if you could 3D print something that's almost exactly what you want and then get the right surface finish with your machining, that's way cheaper. And so that's one of the ways that 3D printing is getting used in conjunction with CNC machining, but you still need the CNC machining to make the part good. You also still needed the CNC machine tool to make the 3D printer. So those are some steps where we're 1, 2, 3 steps away from the CNC machine when we're making the parts. Anyway, so we often use CNC machining to make prototypes. Maybe not the first prototype, maybe not all the prototypes. There's also different kinds of 3D printing that we'll use. So there's the put down the filament kind. There's the laser sintered metal kind. There's the guy with a MIG welder going bzzz, bzzz, building up layers of welded material. That's 3D printing. We've been doing 3D printing for a long time before we even call it 3D printing. So the quick story. One of the methods we do 3D printing, and it's not for prototyping, it's for repair, is a process they call cold spray. It's who's ever heard of thermal spray or plasma spray? So in thermal spray or plasma spray, you basically heat up the metal so that it's molten. You have metal droplets and you fling them at the surface and they stick. That makes sense? That's thermal spray. Plasma spray, they're actually even hotter. Cold spray, that sounds pretty tame, right? Yeah, it's just not quite as hot. It's not quite molten. It's still pretty hot, like 900 C. But they're pushing those bits of powder out and they spray them down on the surface. And so we were looking at a project where, so who's ever heard of the B-1 bomber? You guys know they're still in service? They're still flying around? So they are still in service. However, every single one of them that's in service today is flying with a repaired transmission. because parts wear out, right? You get vibrations and stuff, parts wear out, things move. And so the traditional way to repair those is a guy with a MIG welder. And then machine out the bearing, the slot where the bearing goes, and you put those back together. And so we were on a project, we were proposing using cold spray instead of the guy with the MIG welder. It was like 3 years ago. It's not like that was way back in history. So these are still current processes. These are things that are going on. I thought it was kind of wild. I was in the meeting and there was a big thing on the like up on the screen when we were having lunch, and it's like B1B transmission. I thought, must be a part number for something. No, B1B just meant B1 bomber. I guess that particular picture of it wasn't classified. Anyways, CNC machining, prototype manufacturing. What was the main thing that we learned today? This is important because from what you say, that's what the question on the quiz is going to be. What's the most important thing we learned today? Somebody.
Machining is making stuff by removing material.
Machining is making stuff by removing material. Anybody else got something? Anybody else learned something today? Turning and milling the tool rotates. Yeah.
It's not called lathing, it's called turning.
Except at places where they call it lathing. Like Bausch and Lomb, they call it lathing. You wonder, what do they make? What do they lathe at Bausch and Lomb? They lathe the molds for the contact lenses. What else? I couldn't believe it. I just thought it was a guy that worked at Bausch and Lomb that didn't know what he was talking about, but no, that was the term of the art at the whole company. What else did we learn today? And he learned 2 things today. And his name is Tucker, and he gets an A for today. Don't worry, I'll forget it. Thank you all for being here. Oh, so labs. So if you have a lab today, you either already went or you're going to go. We should have more information later today about the arrival time of the lab kits at the bookstore. In the meantime, we're going to keep doing labs that don't require you to have the kit in hand until you have it in hand. So don't worry about lab kits. We will let you know when they're available at the bookstore.